We'll come back. Let us continue with some standard Laplace transform formulas. Suppose we want to calculate the Laplace transform of cosine omega naught t multiplied with ut for some given value of omega naught. What will be this? Okay, to find that, let me write cosine omega naught t as e to the power j omega naught t plus e to the power minus j omega naught t whole divided by 2. Then this ut. Now this, using the linearity property of Laplace transform, can be written as half common, then Laplace transform of e to the power j omega naught t multiplied with ut plus Laplace transform of this e to the power minus j omega naught t with this ut. Okay, then this is equal to half. Now this first Laplace transform can be calculated in this way. Laplace transform of ut is 1 by s, and when you multiply ut with e to the power j omega naught t, all you have to do is replace this s by s minus this j omega naught. Similarly, the second Laplace transform will be like this. Laplace transform of ut is 1 over s. When you multiply ut with e to the power minus j omega naught t, you have to replace here s with s minus this exponent minus j omega naught t. So that will be same as half. If you multiply this two, denominator will become s square minus j square omega naught square, and numerator will be this s plus j omega naught t. Sorry, no t here, and then plus this is minus j omega naught. Now this 2 j omega naught cancels. We have s plus s 2s and half, which will make it s divided by this denominator s square minus j square is plus omega naught square. So that is the answer. Laplace transform of cosine omega naught t multiplied with ut is s by s square plus omega naught square. In the same way, we can calculate the Laplace transform of sine omega naught t multiplied with ut. And you follow the same strategy as we did for cosine. You will get omega naught divided by s square plus omega naught square. I will leave it as a homework. Next, suppose the Laplace transform of xt is given as capital X of s, then what will be the Laplace transform of t multiplied with xt? we did something similar for Fourier transform as well. So to find this, let me first write Laplace transform of xt is equal to integration of xt e to the power minus st dt, t running from minus to plus infinity. And now let me differentiate both the sides with respect to s. So what we will get here, the left side will become d ds of this Laplace transform, which is given as capital Xs here, and the right side will be the derivative of this integration t from minus to plus infinity. And now by swapping the order of integration and differentiation, I will write this in this way. Then this is equal to integration over time, and then the derivative of this term with respect to s. Now xt is not a function of s, so let me write xt as it is. Derivative of e to the power minus st with respect to s will give e to the power minus st multiplied with minus t, and then dt as it is. So then this is equal to integration of xt, and we have t here, so let me write t here and this minus sign outside, and then e to the power minus st dt from minus infinity to plus infinity. Now this is equal to this minus sign, and this integration is nothing but by definition Laplace transform of txt. So that means Laplace transform of txt is equal to minus of dds of xs. Xs is the Laplace transform of xt. So this is the answer. Let me write. This is minus dds of xs. Great. Now using this property, we can derive the Laplace transform of a ramp function r of t. Recall, a ramp function is like this. It is 0 before time 0, then it increases linearly at an angle of 45 degree with time. So this therefore can be written as Laplace transform of t multiplied with ut. Now Laplace transform of ut is 1 by s, and because of this t being multiplied, we have to take derivative of this with respect to s and multiply with minus sign. This is because of this previous property. Okay, so then this becomes minus, and derivative of 1 by s is minus 1 by s square, that is plus 1 by s square. Next, in the same way, we can ask what is the Laplace transform of t to the power n ut. You can do this recursively. You have t multiplied n times with this function, and therefore what you can do, you can take derivative of Laplace transform of ut, that is 1 by s, m times, and you have to multiply with a minus sign also n times. Now if you perform this differentiation, you will get factorial n whole divided by s to the power n plus 1. You verify this yourself. Again, this is your homework. It is simple to do. Next property, if Laplace transform of xt is capital Xs given, then what will be the Laplace transform of x of at, that is a time scaled version of xt? And here we will take a to be a positive number, because if x is a causal signal and if you take a to be negative, then x of at will not be a causal signal. And in this course we are not that interested about non-causal signals at this moment. So to find this, let me write Laplace transform of x at equal to integration of x at e to the power minus st dt, t running from minus to plus infinity. Now let me substitute at with tau equal to at, so that means dt will be equal to d tau by a, and the limit of integration was t from minus to plus infinity will become tau from minus to plus infinity. So here this will become x tau e to the power minus s, t will become tau by a, okay, and dt will be d tau by a, which I will write outside, and the limit is tau from minus to plus infinity. Then this is 1 over a, and this integration can be written as capital X of s by a. This is, you know, since capital Xs is the Laplace transform of xt, that is xt to the power minus st dt integrated from minus to plus infinity. Now we can replace s here with s by a, and similarly here s with s by a. So this integration is then what we have here, which is capital X of s by A. That is the answer. So this is 1 over A capital X of S by A. Next we will look at possibly the most important property, that is the convolution property, which says the Laplace transform of two signals x1t and x2t convolved with each other is same as the product of Laplace transform of the two signals, Laplace transform of x1 multiplied with Laplace transform of x2. This is again very similar to a property of Fourier transform. Okay, so let us try to prove it. Laplace transform of x1 star x2 is by definition integration of x1 star x2, this multiplied with e to the power minus st dt, t running from minus to plus infinity. Now this is same as integration t from minus to plus infinity, this convolution multiplied with e to the power minus st dt, and now let me put the formula of convolution here. So that will become x1 tau x2 t minus tau d tau integrated over tau equal to minus 2 plus infinity. Next, in this let us manipulate. E to the power minus st is not a function of tau, so we can put this inside this inner integration in this way. Let me write d tau and dt here. So e to the power minus st is brought inside this integration over tau. Next, you see that we have a double integration, so we can swap the order of integration. Let me do it this way. First over t from minus to plus infinity, and then over tau from minus to plus infinity. Here again dt will come before d tau. Next, in this you observe the inner integration is over t, and therefore x1 tau is like a constant that I can write outside the inner integration. I will put it here. Like this. And then let me put, say, a bracket here. Okay, and then for this inner integration, let me substitute t minus tau equal to say p. So here we will have x2 of p, then e to the power minus s, t will be tau plus p, so here p and e to the power minus s tau. Okay, so this is this term, and then dt will be same as dp, so I write dp here, and the limit of integration will be p equal to minus infinity to plus infinity. This is the term inside the bracket, and everything else I will keep as it is. Now here e to the power minus s tau, this is not a function of p, so I will write it outside this inner integration. So I will write it this way, x1 tau, then this outside e to the power minus s tau, then this thing x2p e to the power minus s p dp, p from minus infinity to plus infinity, and here d tau. Okay, now you can see that this term inside the bracket is nothing but Laplace transform of x2. So this I can write as capital X2s, and then the other terms as it is. Now this x2s I can bring outside the integration, so let me put it outside like this, and then this term inside in this integration is nothing but Laplace transform of x1, that is capital X1s, and this x2s I will write as it is, and we are done. This is the Laplace transform of x1t multiplied with Laplace transform of x2t. That is the proof. We are done. Next property, once again, if Laplace transform of xt is capital Xs, then consider the signal x tau d tau integrated from minus infinity to t. This is the integration of xt, and we want to calculate Laplace transform of this, that is integration of xt. What will be this? It is very simple to find out. Okay, notice that this integration can be written as convolution between xt and ut. Why? We told that during a similar derivation regarding Fourier transform. You can check. Okay, so we want the Laplace transform of xt convolved with ut. So that will be Laplace transform of x multiplied with Laplace transform of u, according to what we have learned just now. So this is equal to capital X S, and Laplace transform of ut is 1 by s. That is the answer. Done. Next, again, suppose the Laplace transform of xt is given as capital Xs. Then what will be the Laplace transform of time derivative of xt? Again, we did something similar for Fourier transform as well. So for that, let me write the formula for inverse Laplace transform, which is minus j divided by 2 pi integration of a capital Xs e to the power s t ds or d omega integrated from omega equal to minus infinity to plus infinity, and the value of sigma should be greater than some sigma minimum, that is it should belong to the region of convergence of capital Xs. And you already know that sigma and omega are real and imaginary parts of S. Okay, now let me differentiate both the sides with respect to time. So left side will become dx dt and the right side will become minus j by 2 pi, and capital Xs is not a function of time, so let me write it as it is, and derivative of e to the power st is e to the power st multiplied with s, then d omega from minus infinity to plus infinity. Okay, so now if I put a bracket here, it looks like dx dt is Laplace inverse of this term inside the bracket. Okay, so this is Laplace inverse of capital Xs with s. Okay, so that means the Laplace transform of d dt of x is s capital X of s. So that is the answer. This is S capital XS. Great. The next property is very important and sometimes can be confusing if you do not understand it properly. So please listen carefully. Okay, let me first consider any signal, call it xt, and this need not be a causal signal. So xt can exist even before time 0, and it may exist ever before time 0. Now let me multiply this signal with ut. Okay, so ut is 1 after from time 0, and before that ut is 0. So when we consider this product xt ut, then the result will be 0 before time 0, and from time 0 the product will be exactly same as xt. Okay, so it will be like this. Now a very important fact, when we are multiplying xt with ut, we are erasing the portion of x before time 0 and retaining portion starting from time 0. Importantly, we are retaining the portion of x starting from time 0, that means including time 0. So value of xt is retained for t greater than and also equal to 0. Okay, so this is very important, this greater than equal to sign. Okay, maybe to remind us about this fact, I will put a small minus or small bar below this u and also here, to remind us that when we are multiplying xt with this ut, we are erasing everything before 0 but retaining everything after 0 as well as at time 0. Okay, in textbooks you will find we write only ut without any bar or minus. This special symbol I am putting at least for today, so that you remember the fact that the value at 0 is also considered. Now suppose the Laplace transform of this product is given as capital Xs. Okay, then let us consider the signal dx dt. Okay, consider this original blue signal and let us take its derivative. So at this point derivative seems flat 0, here it is positive like this, after that it becomes negative, here it again becomes 0, then positive. So maybe this is the derivative of signal x. Okay, now again let us multiply this derivative with ut or u minus t, okay, to be precise, and this is dx dt. Now this product dt of x multiplied with ut, that will be something like this. It is 0 here, and starting from this point it will be same as dx dt. Again, the left side is erased, right side is retained, and also the value at time 0, that is also retained. Now we want to calculate the Laplace transform of this product, and the question is, what will be this? Please remember or understand that this is not same as, this term is not same as ddt of xt multiplied with u or u minus. Okay, here we first multiply and then differentiate. Here we actually first differentiate and then multiply. So these two are not equal, and therefore this Laplace transform will not be same as this Laplace transform. That is very crucial to understand. Okay, now so this is what is given, and this is what we have to find out. Now from here, capital Xs is the Laplace transform of xt u with a minus u minus t, and then this is by definition integration of xt u t e to the power minus st dt from minus infinity to plus infinity. However, since this u is 0 before time 0, I will put here from time 0 including time 0. So you may write from 0 minus to infinity, and within this range this signal u is equal to 1. So let me put 1 here. Okay, so this is also called the one-sided Laplace transform of xt, we told yesterday. So this is given, and now we want to calculate this Laplace transform of ddt of xt multiplied with ut, and this will be equal to, in the same way we can write this signal ddt of x multiplied with u e to the power minus st dt starting from minus infinity to plus infinity. However, u is 0 before time 0, so I will put this from t equal to 0 or 0 minus to infinity, and in this range this is equal to 1. So this is what we want to find. Then okay, let us solve this, and let me do this integration by parts. Okay, taking this as the second term and this as the first term. So according to integration by parts rule, we will have first term e to the power minus st, then integration of the second, that is xt, we will put the limits 0 minus to infinity, then minus of integration of the derivative of the first term, which is e to the power minus st multiplied with minus s, so I will put plus s here, and then the integration of the second xt dt from 0 minus up to infinity. Okay, then let us simplify. Acha, here let me put t equal to infinity. If you put t equal to infinity, then e to the power minus st will become 0 provided the real part of s is sufficiently positive. Okay, so it will be 0, then minus, let me put t equal to 0 minus, so we will have e to the power minus 0 minus multiplied with x 0 minus. This is of course provided the real part of s, that is sigma, is greater than some minimum required value. Okay, then this term will be 0. Okay, then this integration plus s as it is, and this integration, you see, it is given here. Okay, and this is equal to capital XS, so I will put here capital XS, which is given. So then this is equal to 0, then minus e to the power 0 minus is 1, so we have x 0 minus plus s capital XS. So this is the answer. Let me put this answer here. Okay, this is equal, let me write here, this is equal to s capital XS minus x 0 minus. Okay, that is what we got here. Maybe I will write this statement once again, because this is very important and sometimes confusing. If the Laplace transform of x t multiplied with u minus t is capital X S, then the Laplace transform of dx dt multiplied with u minus t, okay, this is equal to s x s minus small x 0 minus, the value of the signal at just before time 0. Once again, remember that this is not same as the Laplace transform of ddt of x multiplied with u bar. Okay, the brackets matter. And this this minus sign I am putting today only, just to remind you that the effect of multiplying this signal with x is to erase the portion of x before time 0 but retaining the portion after time 0 as well as at time 0. In standard textbooks you will find this written as u only. Okay, great. In a same way, consider we have a signal xt which is not causal. You can take the derivative of this signal, which will look somewhat like this, and it is again not causal. This is x dot, first derivative of x. You can calculate second derivative x double dot, which will look somewhat like this. Again, this is not causal. Now we may multiply these signals with the step signal ut, which I am calling as u minus t, to indicate that the value of these signals at time 0 is preserved. However, when you multiply the step signals with the signals, then the left side portion of the signal will be erased. Similarly here, this part before time 0 will be erased, and this part will also be erased. Now you may calculate the Laplace transform of xt ut. Here Laplace transform of x dot t multiplied with the step signal, and here x double dot multiplied with this step signal. Let me call this as x's. Suppose this is x's, and suppose this is x prime s, and this is x double prime s, capital X double prime s. Then, as we have learned now, x prime s can be written as s multiplied with this capital X's minus the value of this x at time 0 minus. In the same way, capital X double prime s can be written as s capital X prime s minus x dot, okay, in this case x dot 0 minus, okay, and then this is equal to s. In place of x prime s, I will put this value s x s minus x 0 minus, and then this minus x dot 0 minus. So this is equal to s square x s minus s x 0 minus minus x dot 0 minus. In this way, you can go up to third, fourth or higher order derivatives recursively. In a special case, if this initial value x 0 minus is 0, then x prime s will become sxs. And also if this initial values x 0 minus is 0 and x dot 0 minus is also 0, In that case, x double prime s will be equal to s square xs. But in general, this is the formula. Okay, now one question that you may ask is, what happens if I take Laplace inverse of xs? Will I get back xt? No, rather we will get back xt multiplied with this step signal. So the left side of x will be erased or will become 0 if you calculate Laplace inverse of capital Xs. In the same way, here if you calculate the Laplace inverse of x double prime s, you will not get back x double dot completely. You will get back only the right side portion starting from t equal to 0, and the left side portion before t equal to 0 will become 0 completely. That is because this or this or this, these are one-sided Laplace transform. These are not complete Laplace transform or two-sided Laplace transform which considers the signal starting from -2 plus infinity. Instead, these are one-sided Laplace transform which considers the signal starting from 0 or 0 minus precisely up to infinity. Okay, here is our next property. Consider a signal xt which is not periodic, and suppose the Laplace transform of xt is capital Xs. Now let us copy this signal and let us repeat this pattern again and again to make a periodic signal like this. So this will keep repeating again and again, but this is a one-sided periodic signal. This repeats only in the right side of our timeline, but on this side it is not going to repeat, it is 0. Now let us call this signal as xpt, periodic t. Now what will be the Laplace transform of xpt? Let me repeat that xpt is one-sided periodic, the other side is 0. Otherwise it's not possible to calculate Laplace transform. Okay, now suppose this time period is capital T. That means here also this is capital T. Then xp can be written as summation of x t then delayed by n capital T and summed over n equal to 0 to infinity. n equal to 0 will give xt, this first period. Then if you put n equal to 1, that will give us this second period. And if you put n equal to 2, that will give us this third period, and so on. So therefore, this Laplace transform of xpt is equal to Laplace transform of the sum over x t minus nt n from 0 to infinity, which because of the linearity of Laplace transform can be written as sum over n equal to 0 to infinity Laplace transform of x t minus nt. Now this will be equal to sum over n 0 to infinity, and Laplace transform of this delayed signal will be capital XS multiplied by e to the power minus s t and n. I can also write this in this way, whole to the power n. Okay, then you can take this capital XS outside common, and then the summation of e to the power minus st whole to the power n in 0 to infinity. This is a geometric series and it will be equal to capital XS multiplied with 1 divided by 1 minus e to the power minus st, and this is the answer. So Laplace transform of this periodic signal will be capital XS divided by 1 minus e to the power minus st. Next we shall talk about two very important theorems, initial and final value theorems. Consider we have a signal xt, and suppose capital XS is one-sided Laplace transform of xt. Okay, so that means capital XS is Laplace transform of xt ut, and suppose this is given and we want to know the value of x, the signal, at two particular time instants. Number one at 0 plus, that means here slightly after the point t equal to 0, what is the value of x, and what is the value of x at time equal to infinity or time tending to infinity. Okay, t tending to infinity. We want to know these two values. To find these two values, what you can do, you can calculate Laplace inverse of capital XS and then put time equal to 0 plus or infinity to get these two values. However, if we don't need the complete xt for all time and only these two values are required, then we do not have to calculate Laplace inverse of this function. There is a shortcut, and the shortcut is like this. multiply this x's with s and then take the limit s tending to infinity. That will give x 0 plus. And if you multiply x's with s and take the limit s tending to 0, then that will give x infinity. So notice that this is opposite. For 0 plus s tends to infinity, and for x infinity s tends to 0. And s multiplied by x's is same here as well as here. Okay, let me prove these two theorems. This is called initial value theorem and this is final value theorem. Now the proofs. Let me start from the fact that x prime s is equal to capital Xs multiplied with s minus small x 0 minus. This is the Laplace transform of x dot t, or you may write dx dt multiplied with ut. Okay, so this is equal to integration of this signal dx dt ut multiplied with e to the power minus st dt starting from t equal to minus infinity to plus infinity. Now this you may write as integration of this thing dx dt u e to the power minus st dt starting from time 0 minus to 0 plus integration from 0 plus to infinity of the same thing. Okay, and before 0 minus u is 0, so we need not integrate before 0 minus. Now this u is equal to 1 in this range as well as in this range. So this first integration will become integration of dx dt, and since t is close to 0, e to the power minus st is e to the power 0, which is 1, so I will have dx dt only starting from 0 minus to 0 plus, and plus the second integration dx dt e to the power minus st dt from time 0 plus to infinity. Now this first integration is x with limits 0 plus and 0 minus. Integration of dx dt is x, of course, plus this term I will keep as it is. Okay, now this left side is xs minus x0. Let me write it here. S capital Xs minus x0 minus. Now let me take a limit s tending to infinity on both the sides. Okay, then this left side will become s capital Xs, and this term does not depend on s, so let me write it as it is. And the right side, this also does not depend on s, so let me write it just as x0 plus minus x0 minus, and here I will take the limit s tending to infinity, integration dx dt time 0 plus to infinity e to the power minus st dt. Now notice that time is positive, s is very large, so e to the power a very large negative number, that is 0, so this integration will result in 0. So from here now we can write, also you see that this term and this term cancels, so we have x0 plus is equal to, here limit s tending to infinity s xs, and that is the initial value theorem, so it is proved. Okay, so that was our initial value theorem. Now let's prove the final value theorem. For that, let me start from s capital Xs minus small x 0 minus is equal to x capital X prime s, which is the Laplace transform of dx dt multiplied with u, that is one-sided Laplace transform, and this is equal to, by definition, integration of this product dx dt and u multiplied with e to the power minus st dt, t from minus infinity to plus infinity. Now this is same as integration of this term starting from t equal to 0 minus up to infinity, because before this 0 minus, this u is 0, and here dx dt and u is 1 in this range, and then e to the power minus st dt. Now let me take the limit s tending to 0 on left side, so this will be s xs with this limit, and x0 minus will remain as it is. This will be equal to this right side with limit is tending to 0. Okay, so this is dx dt e to the power minus st dt, t from 0 minus to infinity. Now when s tends to 0, then e to the power 0, this is 1, so we have integration of dx dt only. from time 0 minus up to infinity. So this is equal to dx, the integration of dx dt is x with limits 0 minus and infinity. That is equal to x at infinity, or x tending to infinity to be precise, minus x 0 minus. Now this x0 minus and this x0 minus will cancel, so we will have x at infinity or tending to infinity, this one equal to this limit. Limit is tending to 0 is capital Xs. That is the proof of our final value theorem. Okay, that's it for today. Have a nice day and come back tomorrow.